Ever find yourself wondering how these huge infrastructure projects, the ones really protecting communities, actually get built, especially against something like, well, flooding? So today we're diving into the Boston Barrier Project,
A historic port town, northeast coast.
but sadly very vulnerable to the sea.
Extremely.
Yeah.
Low-lying, always been a risk factor. And that 2013 tidal surge, that was a major wake-up call.
Really hit home, didn't it? Impacting hundreds of homes, businesses too.
Absolutely. That's why it got classified officially as a high flood risk area, and why this barrier project became so, well, essential.
Right, so the Environment Agency, along with partners, they came up with this plan, the Boston Barrier. More than just a wall, right? It had a gate, a fish pass.
A whole system. But a key part, the bit we're really digging into today, is the flood wall itself.
Exactly. The backbone of that flood wall was steel sheet piles, from start to finish, really.
It was, and on a massive scale, you're talking, what, 14 kilometers of barrier?
Yeah, using nearly 6,000 tons of these HZ and AZ steel sheet piles, all supplied by ArcelorMittal.
And that choice, steel sheet piles, it wasn't just plucked out of thin air. You look at the ground investigations, the borehole logs for Boston.
What did they show?
Well, you've got layers, alluvium near the surface, then beneath that glacial till and deeper down Kimmeridge clay. Quite a mix.
Okay.
And the existing ground level, the bed level, was around -3 meters OD, but the design flood level they needed to protect against, plus 5.5 meters OD. Huge difference.
So this varied ground, soft bits, harder bits that favored steel sheet piles.
Precisely, because you can drive them through those different layers. You get that depth, that stability, and crucially, a continuous impermeable barrier.
Right, makes sense. And how does it work?
It uses primary king piles, these super strong HC sections. In this case, HC 1080M A12s. They were 23.7 meters long and made of S460 AP steel, so high strength. Then the gaps between these main HC piles are filled with secondary, lighter AZ sections.
Okay, so the HC are the main anchors, the AZ fill in.
Kind of, yeah. The AZs here were AZ 14700s, shorter, only 17.5 meters long, and a slightly different steel grade, S430 GP.
Shorter piles. Does that mean cost savings?
It does, yeah. Less steel overall compared to using, say, equally long H-beams for everything. But importantly, even though those AZ infills were shorter,
They still have to hold back water pressure.
absolutely, they were specifically designed as part of the system to resist that pressure effectively. It's clever engineering, optimizing the materials. Using those higher steel grades also helped with the hard driving, gave them better resistance.
Got it. The outline also mentions double wall systems near the main gate structure. Why 2 walls there?
Ah, right. Upstream and downstream of the actual gate mechanism, they use these double wall cofferdams. Basically 2 parallel rows of sheet piles.
Okay.
And they were tied together, often with steel tie rods and walling beams connecting them.
Why the need for that extra reinforcement?
It's all about stability in that critical zone around the moving gate. Tying them back limits any potential deflection, any movement in the walls when they're under full flood load, maximizes the resilience right where it's needed most.
Makes sense. And you mentioned adaptability earlier. The wall wasn't just straight lines, was it? There were curves, corners.
No, definitely not. Real-world sites are rarely straight lines.
So how do you do corners with steel sheet piles?
Well, they have special sections. On the left bank, for instance, the design used AZ42 700M piles. They were anchored slightly off-center and then bolted together with a continuous horizontal beam, a walling beam, to ensure the whole structure acted as one unit.
Okay, but what about sharper turns?
For trickier deviations, like specific 10-degree turns they needed, ArcelorMittal supplied special C9 corner sections.
C9s, like pre-formed corners?
Essentially, yeah. Designed to connect standard piles at an angle. And for extra integrity, they were fully welded at the interlock, the join, before being driven down to the required depth.
And the right bank?
That was interesting too. They used special sections fabricated from AZ28 700 piles, which were actually bent physically curved by a subcontractor to achieve an 11.5-degree angle.
Bent sheet piles, wow.
Yeah, it really shows how versatile the material can be when you need to follow a specific alignment precisely.
So dealing with difficult ground, making tight corners, providing massive strength, steel sheet piles really seem to have been the go-to solution here.
They absolutely were.
Yeah.
They offer that blend of strength, adaptability, and importantly, the ability to create a continuous water-resisting barrier that was essential for this project.
And the installation itself, was it quick?
Relatively speaking, for a project this size, yes. They use hydraulic crawler cranes, like a CKE 1350, and initially a 6-ton hydraulic hammer to drive the piles.
But they mentioned hard driving.
They did. So they actually had to switch to a heavier 8-ton hammer to cope with those tougher ground conditions. Shows you need to be flexible on site. They also use a temporary noise barrier, about 5 meters high, during installation.
Right, for noise control. And the overall timeline was quite impressive, wasn't it?
It really was. The first pile deliveries hit the site in November 2017. Work started properly in January 2018.
And the barrier was finished.
By December 2019, so about 2 years for the main construction. That speed is another point in favor of using steel sheet piles in these kinds of defense schemes. Getting protection in place quickly is often critical.
So just to recap the sheer scale, over 6,200 tons of steel sheet piles in total. Different AZ types, those big HZ sections, all coming together.
A huge logistical and engineering effort, definitely. And the result is protection for over 14,000 properties in Boston.
It's quite something, seeing how this specific material, these steel sheet piles, proved so effective and adaptable for such a vital piece of flood defense. And it does make you think, doesn't it, with extreme weather becoming more frequent, rising sea levels, what other kinds of innovative engineering, maybe using materials like this or entirely new approaches, are going to be needed to protect vulnerable coastal communities all around the world? Something to ponder.